We did some examples on, take a line and move it, and take a direction, take a point and move it around. The lamp is about to die, right? We know that. We did those examples, and now we can use the same method in order to do robot kinematics. There we go. So this will be at the same time we will be using our new dual quaternion methods, and we will be reviewing basic forward kinematics for robots. So for some of you that may be also useful. Okay, new. All right. So we are going to be doing kinematics of robots. And we know that in kinematics of robots, everything starts with defining what is the motion of the part of the robot we care about, what we call the end effector, right? As a function of the joint variables, which are the things that we can control, right? And that defines the forward kinematics, and it's also basic to find the inverse kinematics. So it's basically the first thing we need to do in kinematics of robots is to write what we call the forward kinematics equations or direct kinematic equations, right? Forward. And most of you have seen this before, but maybe not in the form we are going to see it, or direct kinematics equations. You can think of them in many different ways. You can think of them as relating the joint space to the Cartesian space, right? That's a way of looking at it. It's a mapping from joint space and when we say Cartesian space, we mean our 3D space, of rigid bodies where we move. Yeah, joint space is just the angles of, for instance, if you have an n-jointed robot in which you have to actuate every one of the joints, yes, for instance, for an n-jointed serial robot. So these are the joint variables that we can control, okay? And I think we did what a serial robot, just one link after the other. The joint space will be an n-dimensional space, in which each of the axes will correspond to one value, right? So it will be the axis for theta 1, this will be the axis for theta 2, theta 3, theta 4, theta n. The joint space is just n-dimensional space, isomorphic to Rn without any, in principle, without any complication if you don't impose any relation between the joints or limits or so on. So n-dimensional space, which means, what this means, it's kind of an abstract look of saying, when you put in the first joint, you move it to theta 1 degrees, and the second joint you move it theta 2 degrees, and the third joint theta 3, and so on. You are just defining one point here. One point will be a set of values for your joints. So for instance, this point will be your theta 1, theta 2, theta n. That will be a point in your joint space. And then you can do trajectories in this space. That means, you may decide to leave all the other joints still and just move one, and that will be kind of a line in one dimension, right? Let's imagine, in order so that we can do some plots, let's imagine a 3-jointed robot, okay? And I'm going to even dare to do some drawing. This is our first joint. So we rotate this one theta 1. And here we have theta 2. And here we have theta 3.
So basically in this kind of transformation, everything will be a combination of rotation and translation, right?
Yeah, somehow it is. I mean,
pure rotation, no pure translation, or
oh, you can. I mean, I'm defining here one with 3 revolute joints, but you could have one of the joints being a prismatic joint, and that will be a translation. Now, from the point of view of the joint space, the angles go from 0 to 2 pi, so those are limited, and the translations go from 0 to infinity.
Yeah.
So in some of them you will have, you know, a certain interval that you will move on. If you have a prismatic joint, in theory, you can go to infinity. In real life, you know, this is also limited. So theta 1, theta 2. So this will be our joint space. And for instance, you say, okay, I'm going to just move theta 1 and leave theta 2 and theta 3 at its current value. Imagine that theta 2 and theta 3 were here. So this was the value for theta 2 and this was the value for theta 1. So if you just move theta 3, if you just move theta 1, you will get a line in your joint space, right? You can create all sorts of curves, surfaces, and so on, okay? But each point defines a configuration. That's probably a good way of looking at it. Each point defines a configuration. That is kind of like a configuration. You know, it's one of the possible states in which the robot can be.
If theta 2 and theta 3 are in initial conditions and we just move theta 1, then it should be from the origin, right? Or
you know, yes, if you define that those are 0, but in this case I'm just starting from an arbitrary point. Yeah, if you were having theta 2 and theta 3 equals 0, then it will be a line coincident with the theta 1 axis. Yeah, you're right. But in this case we were starting from this, you know, arbitrary position, which would be theta 2 and theta 3 initial, and we keep those still and we move theta 1. For instance, it's a possible, probably, you know, one of the simplest motions. So this is joint space. In some sense it's simpler because you just worry about a scalar for each dimension, but you know, it's not so useful for us. So, you know, getting a straight line here doesn't mean you get a straight line in your Cartesian space. That's why we have this mapping here. On the other hand, the Cartesian space is our standard 3D space, but for rigid bodies. So it's really a 6D space. You know, you have rotations and you have translations. So now we need a mapping from this set of joints that can take, you know, any value up to their limits to the motion of a rigid body, and that's what the forward kinematics or direct kinematics gives you. So at the end, what we want is a motion. We want this to have the shape of a motion. We will say, okay, this body was here and it has moved up to here. So if you work on matrices, you want this mapping to have the shape of a homogeneous matrix, 4x4 matrix. If you work on the Clifford algebra, you want this to have the shape of an dual quaternion, which is unit. So that will be 8 components, right? So this is what the forward kinematics is, and there are different ways to do the forward kinematics. Let me tell you 2 of the most typical ones. And if you looked at chapters 2 of the notes and I don't know, some other chapter, you would have seen those. There are 2 main ways of creating this mapping. One is one that has been around since the 50s, I believe, which is the Denavit-Hartenberg based DH based local transformations along the chain. Formation. The chain. So in this method, really what you are doing is I'm going to just draw the same robot but just as joints. So this is your first joint, your second joint, your third joint, and here is your end effector with its own frame. If you use this method, what you do is you create this displacement which will be our forward kinematics, as a product. So you first move from here to here, then you move from here to here. If your joint rotates, you rotate with it, then you move to the next joint, rotate, and so on. That's the Denavit-Hartenberg based way of writing local transformations. So for instance, D is equal to a product of, and if you know the idea of local transformations, of course, it's much before than Denavit and Hartenberg, but what they accomplish is to do this with a minimal number of parameters. So they devise a way that you just have to do Z transformations and X transformations. So the local Z is about the axis, and then the local X is along the link, and you can move just with these Z and X transformations, you can move from joint to joint and from link to link up to the end effector. So it's basically as the product of some Z transformations, Z of theta I di times X ij of alpha ij aij. So if you can define these parameters, the rotation about the Z and the translation along the Z and the rotation along the X and the translation along the X, you have this I equal 1 to n.
Z is along what?
Because we don't use Denavit-Hartenberg, I don't want to waste too much time. This is in chapter 2, but basically what you do is locally you move like this. It's important to know it because you will see in many books. Your local frame at every moment is the Z-axis is along the joint axis, and then the X-axis is along the common perpendicular between two axes. And then the Y will be wherever it needs to be. And then you move to this one, where the Z is here and the X is still along the common perpendicular. And then maybe if your other axis is here, then next one you move to here, you know, and then you move to this one. So you always move either along the Z or along the X. And you keep moving like that, and you just, when we say move, that means write this transformation, which is really simple. This is just an X rotation about the X. Z just rotates about the X, and that's what we call the link twist. And then when you move from here to here, you just rotate and translate along the joint axis. And that gives you your joint variable and your offset and your axis. So you keep multiplying this, which is what the composition of displacements does, and you end up with your whole forward kinematics. This is good for robots that are very square. It's very easy to create a table with all these parameters. It's not so good for design or for arbitrary access. For instance, if you want to, and we have faced this problem before, if you want to write the Denavit-Hartenberg parameters of the thumb, you are in big trouble because it's really hard. The axes are all skewed, and it's hard to give values to those angles in 3D. It's much easier to just locate a line using Plucker coordinates. So that's why we run away from, that's one of the reasons why we run away from this. When you do these products, you will have a lot of cosines and sines of the angles, because this is, you know, what is this? Let me just write these matrices. This is a screw displacement about the z-axis, which means cosine, sine, sine, cosine, right? Cosine theta I minus sine theta I 0, sine theta, we all know this already, that's good. 0, 0, 0, 1, and then oh, there you go. Okay, and then you have a displacement d1 in along the z direction, sorry, di. So when you multiply these matrices, a lot of products of cosines, sines, and so on in your equations. And this is the methodology that is taught in most of the schools. Did you learn this in your school? Yeah? Yeah. There are a few people doing a different methodology, which is kind of the same one we use, and you can do it in matrix or you can do it in dual quaternion. So let me just tell you, you can do this same thing using dual quaternions. You don't have to use matrices. You can write this displacement as a dual quaternion, multiply times this displacement as a dual quaternion. Let me just write it down. We don't use this, but you could do it. You could say D as a dual quaternion is the product, and that means using the Clifford product of a Z dual quaternion of theta I di times an x of alpha ij aij. And we know how those look like. Let me just extend a little bit and just write this using Clifford. You still need the Denavit and Hartenberg parameters, you know, the relative location between the joint axes. This would be the Clifford product, and then, for instance, the Z of theta I di, we know how that is going to look. It will be rotation in the Z direction, right? So 0, 0, sine theta I divided by 2, and cosine theta I divided by 2, plus epsilon. This is always at the origin, so that means the Plucker coordinates of the line defining this axis when we move up to this frame will be 0, 0, 1, 0, 0, 0. So that the S0 part goes away, and then we'll have 0, 0, di, right? Di divided by 2, cosine theta I divided by 2, and minus the I divided by 2, sine theta I divided by 2. So this and this are the same thing in different algebras. Okay? So you can also use the Clifford product to do this product of elements. Advantages, it has less components. Disadvantages, the product is a little bit, you know, well, I'm not sure if the product is more complicated. No, we are so used to do the matrix product that we think it's easier, but you know, you start counting how many products you do. Anyway, so you can do this with the local transformation method. That's not the one we are going to use, but it can be done. If you guys want, we can do an example of this. Let's just do one example, simple one. Okay? And then we'll start working with Mathematica. So make sure you have Mathematica installed. You can download it from the College of Engineering webpage. And some days we will just show the Mathematica code here, because otherwise it's too complicated. Okay, let me go to next page. Let's just do an example. And that's an example of forward kinematics using local transformations. Okay, so here is our fixed frame. Okay, let's put a robot which has the first axis here, S1. Okay. okay, not there. I want it to coincide with, to make it easier, because as I don't have the numbers. Okay, there is the first joint. Let's just do a 2-joint robot. And then how do we want the other one? Let's make it perpendicular. And it's going to go in the x direction. S2, so this distance will be 1, and then this distance over here, let's say is 2, and then this distance over here is 1, and then let's assume the end effector is, yes, along the same line, and it's oriented with, let's just put a little different. Let's say this is our initial x, y, z, x, y, z. So our joint space is at plane theta 1, theta 2. Right? We can write any configuration as a point with a given value of theta 1 and a given value of theta 2. Okay, this robot is fixed. We know what it is. Oh, this distance could be 1, 2. And now we need to pass from this joint space, we need the map to the location of this, position of this end effector, location and orientation. And if we do the local transformation, what we need to do is first we have to move from this local frame to a local frame here, right, at the first axis. So I have more color, that's good. So this is our initial frame. The next frame will be here, Z and X. So in this case, because they are at 90 degrees, this is the common perpendicular, okay? So we have the Z in the direction of the axis, the X along the common perpendicular between axis 1 and axis 2. Our next frame will be with the same X, but with the Z along the second axis. And in this case, we don't need to move away, and then our third frame will be there. So we are kind of simplifying the frames. Okay, so how do we move from this one to that one? What do we need to do? In this case, this is what happens with the dynamic Hartenberg parameters, that usually they put your fixed frame where it needs to be so that it's easy. In this case, we have a translation, Z, X, and a rotation, right? So we have a translation and a rotation about Z, right? We have to move from this point to that point and rotate from X being here to X being there. But we also have a translation in the Y direction, okay? So this is what happens when robots are not at the origin. Okay, so let's see. I guess we'll do the translation first and then the rotation, right? So let's see, should we do the translation first or the rotation first? What do you guys think? So we can move from a frame here to a frame here, right? Let's do an intermediate guy, which have the same orientation, Z, X, Y, right? And then once we are here, we can rotate. So that will be, and we have to use the Y that we never use, right? Y of, sorry. Let me just put first, this is, like, it doesn't matter which math you use, so let's just write it like this. Y of, doesn't change the angle, so 0, 1, that will translate here, and then we do Z, and now we are here, we have to translate by 2, rotate by 90. So pi over 2 positive 2, right? Now we are here. Let me try to draw the robot we were working on while you guys download that and all that. So we were doing just a forward kinematics example. Now I need your help to draw this right. We have the first axis that was around here, right? You have the notes from last day? If not, I guess I can open the notes from last day. Actually, I may, yeah. Let me just open the notes. That way I'll take a quick look to the robot here. Not this one, da-da-da, da-da-da. Okay, so it was at 1, 2, and then 1, 1. Okay. 1, 2, and then 1, 1. So 1, 2 to where the common normal is. Of course, the joint, you know, it's here. And then this was S2. And this was 1 up to this common normal, and then this would extend to the end effector, and this was also 1, and this was oriented as this, so x, y, z, right? X, y, z. So this was the robot that we were doing, and hopefully, so just keep this drawing close to you so that you can check what the transformations I'm doing. And basically we said we are just showing an example of the local frame way of doing it, then we will move on quickly. This is supposed to be at the intersecting the axis, but we say first we will move up to here, so we'll do a y motion, and then we'll go up to here, changing the x to this direction, then we will go up to here, and then we have several transformations here. First we go here, and then we have to go up here at the end. And we had a lot of confusion. Well, I had a lot of confusion. You guys were saying, no, you should use the y. So hopefully this time will be right. Maybe we can put both. No, that's okay. So the first one is the y, and you can follow on the y motion by 1, which means it becomes 1/2 in the dual quaternion. So this is a translation about the y-axis. Then we have a rotation and a translation. There's a way to eliminate this. There is a rotation and a translation about the first z-axis that takes you from down there to up there. This is just a fixed transformation. And then we said, okay, what we are missing now is we need to add what happens when the joint actually moves. And what will happen is that you will have a rotation by theta 1. Okay, this is just a rotation by theta 1 along the z-axis. It goes right after this. So I'm going to show you. We are up to here. Okay, I'm going to show you here. So right at this point, once we have arrived here, now if this joint rotates, everything will rotate with it. So we add this rotation. Imagine the whole robot moving with it. So imagine we are going here, and the whole robot moving with it. Okay. So this will be our z of theta 1. Okay. Everything else doesn't move the configuration of the robot, only the joint motions. So there is where this z of theta 1 goes. We put it right after the z2. Then we have, let me just imagine we haven't moved now. So we have this motion now along the x, and then we will have another joint rotation. Okay. So after this one, we have the motion, rotation and translation along and about and along the x-axis, and then we have the rotation of the second joint, which is a rotation of theta 2, but also about the z-axis, because the local z-axis is always coincident with the joint axis. Okay, so now we are at c5. Okay, so we have rotated this, and then we just need to translate here, and then once you are at this point, make the end effector, so we need to translate from here where it's moved by theta 2. Okay, so now we can even see it better, that now we can, if we rotate, we will just move the end effector and the frame that is, together with it. In this case I have put a minus theta 2, right? All right, so now you have to check if I did this right. Okay, so now we have a translation about the x in order to arrive to the end effector along the x. Then we have a rotation about x of minus pi over 2, and then a rotation about z of minus pi over 2, and that should make the end effectors coincident. Let me just go. So we are there with the same frame x and z, and now we rotate about x, so z comes here, and then we rotate about z, so that rotate about z, so that x comes here to the coincident frame. Okay. All right, so now we have all the rotations. Now in order to create the forward kinematics, we just need to compose all this local displacement, which means multiply the transformations. The way I did it here, I did it in 3 parts, so I went up to joint 1. You get this, and this is the command we use, quadmult. This is from that matrix.m file. It multiplies 2 dual quaternions or 2 quaternions. So it does the Clifford product. Because it's our function, we have defined it, we have to, we can only multiply 2 elements at a time. In a more advanced programming, if you had more, because it's an associative operation, you could have just many and then keep associating inside of the definition of the function, but we are not there yet. So every time you multiply 2, you have to add a quadmult. In this case, if we want to multiply 3, quadmult and then another quadmult. Okay, so that's up to from the origin, from the base to the first joint rotation, and from the first joint rotation to the second joint rotation, then from the second joint to the end effector. You can associate them however you want, and then I just multiply everything together, and this is what I get. So these over here are the forward kinematics equations of the robot in dual quaternion form. Okay. What that means is that now you can solve the problem. Remember, we were talking about going from the joint space to the Cartesian space. You take a point in the joint space, which is a value for theta 1 and a value for theta 2. You put that value there and you get a transformation. And then from that transformation, you can get any point in the Cartesian space. Okay, I'll write that again, because it's really not a direct. You actually do a map from joint space to transformations, and then from transformation to point, it's a second, it's an action of the element on the space. So now we can check what happens at what we call the reference configuration, which is usually is when you have your angles equal to 0. It doesn't have to be, but you check that and you get this. This is a translation, it's not a point, right? So now from this translation, if you take the origin and apply this translation, then you will go to 0, 3, 2. And we should check if that is correct. 0, 3, 2. Because it appears as 1/2. So 0 in the x, 3 in the y, 1, 2, 3, and 2 in the z. So that's fine. It worked, okay. Okay, yeah, it is there. It is okay. All right. So that is the forward kinematics of what we call absolute displacements. And then what you can do with that is create any displacement from the base of the robot, wherever you have defined your base frame, to the end effector frame, giving values to this. Another thing you can do is you can plot what we call the workspace, which is the set of all possible displacements of the end effector. The way we are doing it. If you want, you can take that at the set of all possible locations of the center of the end effector frame, or you can apply it to any other point once you have the displacement, right? So what I do here is I just take this. This is not exactly the point, it's just the dual part of the dual quaternion. From here, it's the point, you have to find it from there. I give values to theta 1, I give values to theta 2, and I create a table, and then I just plot it. Now this takes a while because it's 50. Okay, so it's 50 times 50, right? Because for each 50 you have, you have 50 times 50 points here, and this kind of that's why it's moving kind of slow. You see, there it is. Of course, here you have the effects of
This is the workspace.
This is not the workspace exactly. This is the plot of the x. I'll write it right now. Okay, so we have this plot. It's not the workspace, but it's somehow related to the workspace. Let me show you how. And that also ties with the comment I wanted to do. Okay, so we have done the forward kinematics for this robot. Absolute. We call this absolute forward kinematics because then we will compute a relative one. Okay. Which means for any values of theta 1, theta 2, we have a mapping now that will give you the motion, the displacement. Gives you d. All right. I mean, not put a matrix. Let me displacement. Displacement of the end effector. It's not giving you the end effector, it's giving you the displacement of the end effector. And many times we tend to identify, the end effector with the displacement of the end effector. But for instance, when you are talking about a matrix, right? If this is what you get from the forward kinematics, this is the rotation part, and this is a translation vector, and then you say, where is the end effector? You say it's here, right? This is the point of the origin of the end effector, right? So if this is your displacement d, it's kind of easy to see where this point is. It's just this vector d. This was not the point where the points were. This is the displacement you apply in order to get that point, right? This is with the matrix. With the dual quaternion, so here you have our d, we can put a hat. In dual quaternion, what we get is d plus epsilon d0, if you want, so 2 quaternions. That plot over there corresponds to plotting, let me see if I can, this is also, that's okay. So plot in Mathematica, what we would like to do is to plot these 6 components, but we don't have a 6-dimensional plot yet, so we just take 3 components, and the 3 components that are most closely related to the points where the end effector will be are the upper 3 values of the dual part. Let me just put so this will be d0 plus d1i plus d2k plus d3j, remember all the components, plus epsilon, d4i plus d5j plus d6k plus d7. These are the 8 components of the dual quaternion, right? So what I want to take is this vector in quotes, okay? This dual part of the vector. Plot in Mathematica is d4, d5, d6. d6 as a function of theta 1 and theta 2. So what you get in these values? It's like, okay, yeah, there is no reason to do this. If you wanted to do, and of course by workspace there are many things that we understand by workspace, but if you want to do as a workspace the location of the origin of the end effector frame, so this point, where this point can be, what you need to do is you need to take your d and take this point, which is the 0, 0, 0, So in order to plot, we can do it, it's not so big of a deal. So let's just do it. In order to plot the origin of the end effector we need to see where it goes. So how do we want to call that point? Let's call it P. Okay, we have P. All the positions of P will be equal to our D. Little p, D conjugate with the conjugation number 4, right? The one that cares for points. Okay? Little p is 0, 0, 0, 0, 0, 0, 1 plus epsilon 0, 0, 0, 0. Right? In dual quaternion form. It's the origin. It's here. Okay? And this indicates it's a point. So let's do that. We can do this in Mathematica. That should be fairly easy. So we just need to do the fourth conjugation on D, and then calculate the value. So it can be even done like this. So how do we call this thing? This is Fk, right? Fk. So let's just do Fk conjugate. Let me just put a note. Is it a note? We will just plot the points. Yeah, delete. We are just going to plot the points. So let me put a note here. Plain text. Plot of the origin of the end effector. So all possible locations of the origin of the end effector when you give values to theta 1 and theta 2. Okay. Okay, first thing we have to do the Fk conjugate, and we have a function in the matrix.m to do that, which I forgot the name for. Let me see if I can open here. Matrix.m. Okay, make point, conjugations were somewhere in here. I think I'll document this because otherwise it's just kind of hard. Common normal, quad mult, quad conj 4. Okay, this is the one. Okay, quad conj 4. Quad conj 4 of Fk. Okay, and now what we have to do is we need to do that product. So we need to do the quad. So P in the fixed frame, let's say, is going to be a quad mult of Fk with I have to define little p. I need p in the moving frame, and that will be just 0, 0, 0, 1 plus epsilon 0, 0, 0, 0, right? So now we need to put here PMF comma Fk conjugate. Now this could be a little bit long, okay, because it's not simplifying, and Mathematica, Maple and all those are, well, these are programs that are well known for not simplifying as they should. We can put a simplify command in front. See what happens. But it doesn't matter because look at that. You see, could have done that from the beginning, right? All right, so this is the set. This is 1, 2, 3 components. This is a set of all possible locations of the origin of the end effector frame if you give values to theta 1 and theta 2. So now we are going to give values to theta 1 and theta 2, which we already have up here. You can reuse the epsilons. Okay, let me show you what we are getting. We are getting something with epsilons. If we write it in here, what you get as a result is it's a dual quaternion that will look like 0, 0, 0, 1 plus epsilon, and then the location of the point should be here, P0. So now we need to rescue this point from here, get rid of the epsilon basically, okay? Because we need to plot, Mathematica doesn't know how to plot things with epsilons. So this just gets rid of the epsilon, doesn't do anything else, except that we just want the first three components. We don't want the fourth component, because we cannot plot in 4D, so let me just take 1, 2, 3. Okay, now we have the point, PFFP. Okay, and we don't need to see that, and we know it's long. Hopefully it will plot now. It seems that it's plotting because it's, oh, there it is. So you see the difference between this one and the other one? They're not exactly the same, it gives you. This is the set of all, if your angles are allowed to go from 0 to 2 pi, let me just go back there to our plot. You are rotating here and you are it's like a torus basically, but in this case you cannot see the hole because this distance is equal to that, so the hole it's kind of. And you can put more points. Here is not showing many points, I just put 50 times 50, so 2. It's kind of.
Basically, is it a workspace or what?
This is the workspace.
And the other one was, what is the difference between the two of them?
The other one is something we call the workspace. And this is, when you calculate, you say, the forward kinematic gives you the workspace, but the other thing is a displacement. It's not a point in the Cartesian space. It's a displacement from your origin to whatever point you select. And I know it's a subtle difference. It's a subtle difference. Let me see if I can illustrate that. So you see, once you have when you do the forward kinematics, you get, for instance, let's say the typical one so that you relate to it. When you do the forward kinematics, you get a matrix. That's not a point, that's a displacement. Has a rotation and a translation part. Now you can take this matrix and apply it to any point, and then you get a point on the workspace. But you can argue that this is also the workspace of, this is the workspace of displacements, and the other will be the workspace of points. Okay. Once you have the workspace of displacements, then you apply it to any point, and you get the workspace of points. For instance, let's take the same robot that we were solving, right? Imagine that instead of the center of the end effector, you want to put a tool here, a screwdriver, and you want to see what is this point. You can.
We can apply the workspace of the displacement to find the
any point.
Position of any point.
Mm-hmm. So now you say, okay, I want this point. Okay. So then you can, apply this action to that point, and then you will know where that point goes all over. So this mapping is really, if we just give this matrix, this mapping is really from the joint space to the space of displacements. It's kind of abstract, okay? You need to do one more step in order to apply it to points, because this is not a point. Well, it's a point of your group, and it's a different algebra.
When we construct the displacement workspace, we use the forward kinematics from axis to axis to axis.
Yes.
Where we stop.
Well, this is the absolute displacement, okay? So that goes from one frame to another frame. And that is a displacement. But what we create is a displacement. So yeah, we go up to that frame that we define. Then from there you can measure any point, right? So let me just, I don't know if this is going to help or not, but here we have our joint space, okay? Which each axis is one, we always get detract and then we never have time to finish anything. Anyway, each axis is one of the coordinates, right? Theta 3, and then you have 6 degrees of freedom, 6-dimensional space, and every point is, the set of joint variables, right? And then you do forward kinematics, and then you live in the space of your displacements. When we are doing dual quaternions, this is a quadric in a 6-dimensional space, okay? 1, 2, 3, 4, 5, 6. Okay, so you put values here, you get a point here in the quadric. You get a displacement. For each set of values here, you get a different displacement. Now you can take this displacement and act on points of your space. So it's the group action. So this is the forward kinematics, and this is the group action. And now you take this displacement, apply it to whatever point you want. For instance, the point that was here, and then you move it to whatever you want, and then you can give. So you actually get all the points of your Cartesian space, and you can get the points, and you can also get the the rotations, the change in orientation. Okay. Sorry. Even forward kinematics and workspace become complicated when you look at it really in detail. It's like, oh yeah, the set of all possible. It's the set of all possible displacements. If you are giving just it's not the set of all possible points unless you apply that to some points. Okay. All right. Man, I never thought so much about the workspace until now.
It also take care of the singularities and everything in that one.
No. Well, some singularities are representation. Depend on the representation you use. Those you can get rid of when you use, another.
It is mapping and stuff like that. So it is taking care of those or no?
Okay, singularities do not appear in the position workspace. So whatever positions you can reach.
Despite it can move or not.
It doesn't tell you how smoothly you can move from one to the other. That's when you can run into a singularity, okay, and on singular points. So that is not identifying the position workspace. Then you have to look at the velocities, and you can look at that through the geometry, but it's like a smoothness problem basically. Okay. So one obvious singularity is the boundary, and that you can get from here, but not the internal singularities. Yeah. So you see, this is the set of all possible points at more or less, up to the precision of this representation, that the center of the end effector can reach. This is the set of all possible. These are 3 coordinates of your displacement. Imagine you take your 6-dimensional quadric, and you take just 3 of those components. It's like a projection of part of your quadric on the 3D space. And unfortunately, we cannot do better than this. So this is kind of useless, but the other one is good, right? The other one is useful. Okay. So this is for absolute displacements. I wanted to finish today relative displacements too, because that's what we will be using. So it's kind of straightforward. It's the same that you do with a matrix, and now that you have all that file, you can use it in Mathematica. So we had the absolute forward kinematic that means you come from your origin of your fixed frame to this moving frame. So it's what you get with the absolute forward kinematics is this displacement B. Okay. In matrix, in dual quaternion, in whatever, in axis, angle, representation, in vectors, whatever you want. Okay. Now we are interested, because it simplifies the problem, in what we call the relative forward kinematics, which stems just from the definition of the relative motion that we covered in the first chapter. If you remember, what we will have now is we will still have a fixed frame that we will measure from. We measure always from our fixed frame, but now we will say, okay, our robot, the frame attached to the end effector of the robot was here before, now it is here, and we want to know this motion. Okay. So imagine that this is known as our reference configuration. It's an easy pose where everything is straight or everything is collapsed. So this is just an easy pose that does not, let's call this D0. And now we want to know what is this displacement from this reference configuration to any other one. Okay. And this is called D0I, and this is pose. If you were able to define this as di from using the absolute displacements, then this would be D0I from 0 to I, and this is just di D0 inverse. That's the way it's defined. So it's basically you come back here, D0 inverse, because you operate through the right. You come back here with D0 inverse and then you go to DI, and that's the same as doing this. Okay. So this is the forward kinematics that we will use, from a reference configuration to another one, not from the origin and going through the chain, but assume you already know your chain and move from there to another position. That has the advantage that it eliminates all the fixed parts. You know, what you end up is only with the motion along about each joint. Okay. So it can be proved, and it's in the notes. Be proved that if we use this, you don't need to be going through the chain and knowing all the angles between the chain, but for a serial robot with end joints. So here we have S1, S2, S3, up to Sn, and then we have our end effector. Okay. This relative one, D0i, is just the product, the composition of rotations about each joint. Okay. It will be equal to S1 of theta 1, Sn of theta n. Okay. You know, this is in general, so basically you don't need to go up to this joint. If you know the coordinates of this joint, you create a transformation which is a rotation about this particular joint. You know where they are in the reference configuration with, let me just say that, S1, Sn at the reference configuration that you move from. Okay. So if you know where your reference configuration is, which usually is known, then you create this rotation or translation about the joints at the reference configuration. You multiply them all together and you get the relative motion. If it's intuitive, if you think of moving the last one first, because we multiply through here. So you are here, you move through this one, you know, you will go somewhere, and then you come here, you move that moves both of them, and you keep moving backwards, and that will move your whole robot. Okay. And this can be implemented very straightforward in dual quaternions, because it's very easy to know the rotation about a joint. You just take the Plucker coordinates and multiply times the cosine and the sine of the angle, right? So let me just say that using Clifford algebra, and I should say not just Clifford algebra in general, but our Clifford algebra, you know, S1 of theta 1, and I'm going to put a hat saying I'm using dual quaternions now. Remember what that is cosine theta 1 divided by 2 plus sine theta 1 divided by 2 S1, with S1 being the Plucker coordinates of the joint. It's as easy as this. This is a rotation about S1. You just put one for each, and if it's a translation, let's imagine that if joint K is a translation, it's a slider, it's a prismatic joint. Let's just talk properly. It's a prismatic joint. Okay, so then S K of, let's say, TK will be equal 1 plus epsilon TK divided by 2 SK. SK being the direction, okay? SK equal SK, direction of the joint, plus epsilon SK0. Okay, the Plucker coordinates of. So it's very easy to write these, what we call screw transformations about each joint, multiply them and get the relative forward kinematics. And we are going to do that as an example. Just two expressions for normal joints. You can create the same expressions for spherical joints or for cylindrical joints. It's also very easy. There are in the notes, that you have them there. There are expressions for the cylindrical, for the spherical, I think even for the universal joint, and they are all fairly easy. Okay, let's try it. So I'm going to put here mathematical example. And we can see how the workspace of relative displacements is different from the workspace of absolute displacements. Oh, actually, let me say something else. I didn't put the bottom line, right? So the relative forward kinematic equations. Fk rel equal to S1 of theta 1, Sn of theta n, and in fact, this is what most people use in robotics when you work, when you have to deal with robotics seriously. Not many people use the dual quaternion, but they use this in matrix form. Okay. You can recover the absolute forward kinematics very easily here. So the one that we were doing before. You can use the same methodology. You can do the relative forward kinematics, and then just multiply times the displacement to the initial configuration, which we just did the. If this is the 0i, which was the I d0 inverse, we just multiply times d0 here, and that's it, times g. Let's just call it g. Transformation to reference configuration, and we'll do that also in to reference configuration. Okay. So if you really like the absolute, it's easy to recover them. It's just a constant transformation at the end. Okay. Let's just try with the example we had. Okay, so what we need to do now is we need to create the Plucker coordinates of. Let me just put a section here, and to do that you just go here and you just do format style section. This will be 3, right? Relative forward kinematics equations. So first thing we need is the Plucker coordinates of the axis at the reference configuration. Don't forget. Let us consider the reference configuration as the one we had here. Okay? This is our reference configuration. So this would be the Plucker coordinates of S1. It's in the z direction and at 1 in y. You'll have to give me the data because I cannot see it. Okay? So let's just call S1 equal to 0, 0, 1. I'm not sure if I need to use the epsilon or not. To use that, I forgot. Well, we will see. Plus epsilon, and now we have what was 0, 1, 0 cross 0, 0, 1. Okay, so that is these are the Plucker coordinates of S1. Now I can put S2 right after. S2 will be equal to 1, 0, 0, right? It was in the x direction. And what is the point on the line? Line 1? You guys have that? No? Okay, let me look at it. So that's at 0, 2, 2, right? A point on the line is 0, 2, 2. 0, 2, 2, cross 1, 0, 0. Okay, so there we have S1 and S2 and Plucker coordinates. And now we just need to create a dual quaternion that it's a rotation about each of these axes, one for each. There is a function for doing that in the matrix.m. And let me see, where is the matrix.m? I always forget. Quad mode, quad conj, dual make line, make point, make dual vector, make quad. Okay. And let me see the debug. Okay. Okay. So we'll use this make quad, or this make quad e gives with the epsilon. So the make quad e, but we need to create this as lines. Okay, let me just modify this and put them as two vectors, okay, instead of the epsilon, because that's the way we will. Well, let me leave it like that so you can see them, and then I'm going to copy and repeat them without the epsilon, just as two vectors, one after the other. Okay. So that what we do is the first vector is the one without epsilon, and the second vector is the one that corresponds to the epsilon, and yes, gives you that. And now we can say QS1 make quad E. Now you have to put the line S1, then the angle will be theta 1 that you rotate, and then the slide, which is 0 because it's just a revolute joint. And there you have your. This is a rotation about that particular axis, okay? And then we can do the same thing for QS2. Make quad S2, the line, the angle, theta 2, and then the slide, which is 0 because it's another revolute joint, and that is this is a rotation about the second joint axis. And we multiply this and we get the forward kinematics. You see, it's easy. I'm trying to sell it to you guys. I'm a salesman for Clifford algebra. I'm a saleswoman. So now we can do the forward kinematics. FK rel is that easy. Quad mult, QS1 and QS2. And simplify because, of course, Mathematica. Alright, so that is the relative forward kinematics equations. In this case they are a little simpler. You know, if you think you are just thinking about motion from here to there, so you don't have to worry about what happens when you go from here all the way to there, you know. You are just looking at the motion really. Now, the other one was the motion too, but the other one seems more like you are looking at the points. Alright, that's it. What else can we do with this? We have a few minutes still. One thing we can do is check if really we have done it well. Let's just post-multiply by the transformation to the reference configuration in order to see if we get the same as before, right? So let me just put a note and say, let us post-multiply by the transformation from the origin to the end effector at the reference configuration. We should get the absolute forward kinematics by doing that. And we have that value. We have it here because we have found it here when we said, where is this over here is the transformation to the reference configuration. So it's this FK0. So we just take our FK rel, we multiply it, quad mult, by the fk0, and now we should compare this to fk and get the same thing. So let me subtract them and hope for the best. Simplify. Oh, good. Sometimes I feel like, you know, I'm working on the doing these examples without knowing what's going to happen. Okay, it worked. Okay, now you believe it, right? Before it's like, oh, what is she saying? Okay, relative times the transformation to the reference configuration equal to absolute. But you see, the relative is nice. We use it especially for design, because in design, and that's what this class is about, what you care is where your joints are, except Jimesker, who cares about where the links are, because he's doing the optimization. But you care, in order for you to get a motion, you care where your joints are. You don't care what happens to go to the end effector from the last joint or things like that, okay? So this kind of simplifies a little bit your problem. All right? We can look at what is the, you know, we could look at the plot of this, but, you know, it's kind of abstract, so. So with this we have the forward kinematics, relative and absolute. We know how to use the dual quaternions. But we have a few minutes, so what do you guys want to do? You want to look at some plot at some point? You want to look at a different robot? No? Nothing? All right. I'll give you some homework assignment next day so that you can practice. I know you are, just willing to. It's like yes. He's not enrolled, so it's like yeah, keep them. Yeah. So you can, it will be simple robots that will be fairly easy to create this, and you can just use the same file. Just change your numbers there, and do your plots, and maybe you can. Oh, another thing we can do is we can do trajectories. Let's do that. Trajectories. Let me talk briefly about that. Oh, shoot, no. How do you unextend? Undo? I'm in the first page.
Unextend. Undo editing?
I don't know. It didn't change anything, right? So I think it undo. Anyway, extend page. Maybe I was right. I don't know. Did it erase anything here? Because I thought it was longer. Maybe not. Anyway, sorry if it did.
No, we can repeat it.
Yeah, exactly.
No.
What happened?
Not by writing, by the options. Undo and repeat. Okay.
This one, what is this?
Redo.
Now undo.
Oh, he's not doing anything, so I guess we are fine. Okay, let me just talk. You know what?
Yeah, I think that's the last one.
Ouch! You see, yeah, now it's taking things. Configuration, yeah, okay. Yeah, anyway, okay, let me put it there and stop playing. So we did the workspace, which is look at all possible values of theta 1 and theta 2. And usually they don't go from 0 to 2 pi as I did, but there are some joint limits, so it won't be like the whole sphere, because of physical limitations. But another thing we can do is we can create trajectories in our joint space and see what happens, what kind of trajectories that creates in our Cartesian space. So that means this is theta 1 and this is theta 2, this is the joint space, and say okay, I want to move both of them at the same time. So starting from 0 and going up to a certain number, that would be like this one, right? Well, that's supposed to have 45 degrees. But you can create any other trajectory and see what happens in your Cartesian. So that means, when theta 1 is 0, theta 2 will be 0, when theta 1 is this, So you're moving both of them simultaneously, and then you can look at what happens at the end effector frame. Okay, where is your end effector going with this motion? And it's very nonlinear, so it's not intuitive. These are trajectories in the joint space, or you can do the inverse. Okay, so these are trajectories in joint space, and then what you get here, you know, will be crazy motion. Or you can just create a trajectory here and see what happens here, right? Now I say, no, I really want my end effector to go, you know, from this point to this point, but I really want it to go in a straight line, if that's a straight line, right? So what happens in the joint space, okay? What happens here? What kind of trajectory will I get for my theta 1 and theta 2 in order to accomplish that? You see, I knew we were missing something. We haven't talked about the inverse kinematics, but what this uses, it uses the inverse kinematics, which is the inverse mapping, right? Here you have the forward kinematics that you can use. Here you have the forward kinematics to the -1, which is called the inverse kinematics. And we talk about what it is in the first day, but for the inverse kinematics, you use your forward kinematics mapping. You just solve for different variables. Inverse kinematics. Now you have your forward kinematics, which is d as a function of theta 1 to theta n. Everything else is known. These are just parameters that you can give values to, right? So this is given. So given this one and a desired position, the I don't know how to call it, the desired. So I say, I really want my end effector to be there, and I know what kind of shape our robot has. Now you have to solve for these values. So for theta 1, theta n, what values you need to give here in order to get that displacement. Okay. So we have already done the hard job, which is finding that. That's what we believe. The problem of this is a very nonlinear problem, because you can just look at our Mathematica file. You know, here this is the forward kinematics. Now you are asking to solve for theta 1 and theta 2 here. A lot of cosine, sines, things that are not handled very easily, because you know cosine and sine, they are these kind of difficult functions. We have a lot of trigonometric tricks to solve them, but they are really, you know, if you think of polynomial, you know, it's not very simple. Okay. So we can try that. Why don't we do an inverse kinematics first? We just put a little section, and we will try to do the inverse kinematics for this robot, and that will be, I think, is 5. Inverse kinematics. Now we take given the forward kinematics and a desired displacement for the robot. For instance, I want the robot is in the reference configuration, I want it to go there. Find the angles, find the required angles at the joints. All right, so we are going to cheat, because sometimes you may, in a robot like this, which is a small robot, you may get a position that is not in your workspace, it's outside of what you can reach. So let's just give some values here, create a desired position, and then, you know, solve for the angles that you need again. Okay. Let us create a desired transformation. So let's call it d desired equal to fk. It will be a relative because it's a little bit simple. And when we put this line and this dot means we assign values in Mathematica. Theta 1 0.2, I'm just inventing some values. Theta 2 going to minus 1.7. All right. So this is our desired transformation. We want the robot to go there. Now we need to solve for that. So basically, you know, The easy way would be to just equate this to that and solve, right? Well, let's try, see how long it takes. First thought, equate fk rel to the this and solve for the angles. Okay. All right, so let's see, fk rel minus the this. Now I want to get rid of the epsilons because, you know, Mathematica is going to try to solve this algebraically using Grabner bases, and epsilon is going to bother it a lot, so we need to get rid of the epsilons, and there is a matrix command for that, I believe. I closed it, I guess. There's a way to pass. Forgot my own commands. SEPQ. Yes, SEPQ. Okay. So we apply this SEPQ command to this, and it will give us the 8 components separately without the epsilons. Okay. So now we have 1, 2, 3, 4, 5, 6, 7, 8. Each one of these corresponds to equating the corresponding component of the dual quaternion. So 8 equations in 2 unknowns. You know, it's not going to be able to solve it, obviously. So we can just take 2 equations, right? 2 equations in 2 unknowns. Let's just take 2 of them and see what happens. It's not a simple problem, okay? 8 equations in 2 unknowns. Okay, what do we want to try? And this is what the inverse kinematics says. It's always, what do I try in order to solve? There is no methodology in general to solve it. So, I don't know. Should we take 2 components and try to solve? See, take these 2 and solve for theta 1 and theta 2. See what happens. Let's see. Solve. Oh, let's give a name to this. Let's just call these equations. Solve EQS 1, for instance, and EQS 2, right? EQS 1, EQS 2 equal to 0, and then we solve for theta 1 and theta 2, right? Theta 1, theta 2, and these brackets, the curly brackets, just, you know, separate the variables you are solving for from the equations. Oh, there it is. It's giving us values. Okay, I was complaining so much. Does it give us the right values? 0.2, yeah, and 1.7. Well, it's giving us 2 solutions: 0.2 and minus 1.7, and then, you know, the other one. Hey, just taking 2 equations worked. It doesn't always work, okay? We were lucky. I wanted it not to work, but now it did work anyway. But you see, so this is the inverse kinematics problem. Given the displacement you want to attain and your angles. Now you put your angles in this, you put these angles in your robot, you can get this. And you know, the same that we do it for a point, you can create a whole trajectory. You know, this is the motion I want in my end effector. Let's see how can I back to the motion in the joint space. Okay.